All right, we are on chapter 6 now, and chapter 6 is all about the periodic table. We are obviously going to start with 6.1, which is about organizing the elements. So we're going to look at how the kind of a little brief history of how this organization that we have today occurred and what that organization really tells us or what it means. And we're going to also look at the three main classes of elements, metals, nonmetals, and metalloids. And then in chapter 6.2, we're going to classify the elements. So we're going to learn about these different groups. So we're going to learn about the alkali metals, the alkaline earth metals, the transition metals, etc., etc. We're going to learn what all these different groups are, what their characteristics are, why they are grouped like that. And finally, in 6.3, we'll look at periodic trends, like how atomic size, the size of the atoms changes as we go across the table. We're going to look at lots of different trends of the periodic table in the last section. That's my favorite section. But first we have to get there. So early chemists organized the elements that they knew about into different groups based on different characteristics. There were lots of different chemists trying to figure out what was the best way to organize these elements that they knew of. They had only identified 13 elements by the 1700, early 1700s, and they all were expecting that more elements existed, but they were unknown. And then everybody was trying to discover more new elements, and that discovery started picking up, and the more they got, the more they realized, okay, we need a way to organize these. So we'll start in 1869. There were around 60 elements, and there was a Russian chemist and teacher named Dmitri, there we go, Mendeleev. And what he was doing is he was writing a chemistry textbook for his students, and he was trying to figure out, how do I organize these 60 elements so that I can show relationships amongst them to my students, and I can show how each of these different properties that they have are related, how they're different. So what he did is he wrote all of the properties of each element. He wrote the element name and he knew of, like the 60 that they knew of. He didn't know of all of the elements at that time, like I said. So he wrote the element name, he wrote some properties of that element on note cards, on all these 60 different note cards, and then he organized the elements based on certain characteristics and based on atomic mass. So there were some, obviously, since he only had 60, and if we look at our periodic table, we have about 120, 118 to be exact. There were a lot of question marks. So he left question marks in between elements that he thought, like, there probably exists an element here, but we just don't know about it yet. So he had a lot of question marks. But this is different than today's table. So he organized by increasing atomic mass. Let's look at our periodic table today, and we see that is not the case. Because let's look at just this simple example right here. There are a couple examples of like this on the periodic table. Actually, this might be the only example. I swear there was one in the transition metals, but now that I'm looking, I can't remember which one it is. But anyway, here's one, maybe the only example. I'll have to look that up. I can't remember. So one example is tellurium and iodine. So if you look at their atomic masses, remember atomic mass is the larger number on the bottom, and the atomic number is the smaller number on the top. Remember, this is our relative atomic mass based on natural abundance of the isotopes of tellurium and iodine. But if you look here, these are not in order. Iodine should be before tellurium, because if we were doing Mendeleev's system, these two would switch places, right? 126.9 should be before 127.6, but that is not the case. So today, the modern periodic table is organized based on the atomic number, but before, Mendeleev based it on the atomic mass, but this is not the case anymore. The reason that that iodine is not before, that these two don't switch places, is because iodine has more in common with all of these, with the group, well, not that actually. I did it again. Just with these ones. With these halogens, remember that word halogen? Probably, I hope you remember that word. It has more in common with the halogens than tellurium does, right? We're going to understand what that means more later. But today, the way the modern table is organized is based on increasing atomic number instead of atomic mass. All right, but we have to talk about Mendeleev when we're talking about this, because he wasn't totally wrong. I mean, the table is still not, I think all but maybe these two are organized by atomic mass also. However, they're not all of them. So that's why we say we organize them by atomic number rather than atomic mass. All right, one more thing about today's periodic table. It's organized by atomic number. So, 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. But it's also organized into, remember the word periods? I've already used that. Periods and groups. Remember that the periods tell us that there are 7 of them. Here they are. They're this way. 1, 2, 3, 4, 5, 6, 7. We have 7 periods, and they are actually, remember, they are associated with the principal energy level, right? So we have N equals 1, N equals 2. We just learned this in chapter 5. You understand N equals. All right. So we have 7 principal energy levels and 7 periods. We also have them in different groups, right? So we have 18 groups on the periodic table. We have the A groups, 1A, 2A, and then we have all the A groups continuing over here. So we have them in these A groups, and we kind of talked about this before. We'll talk about it more when we actually talk about the groups in 6.2. But remember, we have them put into these different columns, and we've only kind of very briefly touched on them. But these different columns, also all of these in column 1A, share characteristics. They are all a certain type of group called the alkali metals, actually, which we'll learn later into 6.2, like I said. They all have characteristics. All the alkali metals have similar characteristics. The second group, all the alkaline earth metals, they all have similar characteristics. All these transition metals in the middle, they have similar characteristics. And of course, we know another good example is the noble gases. They all have similar characteristics as well. These elements occur in what's called a periodic pattern, or periodic. It's sometimes called periodicity or a periodic pattern. So what that means is they occur, or certain characteristics occur every so many elements. So what I mean by that is, if you look at lithium is number 3, but it is very, very similar to sodium, which is number 11. So there are 8 elements in between there, right? We have 1, 2, 3, 4, 5, 6, 7, and then we get there. So there's 7, I guess, in between them, but and then if you look at potassium, number 19, same thing. Number 19 is very, very similar to sodium and lithium. So we go through all these elements, blah, 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 blah. Excuse me, I did that on the wrong row. Magnesium, 12. So we have 1, 2, 3, 4, 5, 6, 7, and then 8 again here. So we have this periodic means like occurring every in a certain cycle. So we have this periodic trend in these elements, and that's why we have them grouped in these certain groups that we have them grouped in. It's called a periodic pattern, or a periodicity. All right. So there's a little preview here. The reason that we have these trends, we're not going to learn about this I think we learned about this in 6.3, but what causes these trends? What causes this periodic pattern that we see in the periodic table? I will tell you that you could probably guess what it is. It starts with an E. Electrons. The electrons of the atoms, of course. Remember how important, I told you electrons are so important. Electrons determine this periodic pattern that we see. Electrons determine that all of these elements, and I'll just include us in there, all of these elements are similar. All of these elements, the noble gases, because of their electrons, they have similar characteristics. Because of this group 1, all of their electrons, the way that their electrons are arranged, they have similar patterns. So we're going to get to this soon, but that is the reason that we have this periodic trend that we see in the periodic table. Okay, so there are moving on a little bit, there are 3 main classes of elements. So this looks a little different than the periodic table that I showed you before, where we had each of the groups named. So first we need to learn, because if you look back at this periodic table that I showed you, let's bring it over here actually. Here we have alkali metals right here. We have alkaline earth metals. We have transition metals. So we have all of these different types of metals, which are all the yellow ones here. And then we have different types of non-metals, which are the blue ones. And then we have different types of metalloids, kind of splitting those two. So we're not talking about these groups yet. We're still not talking about the groups. What we're talking about is just 3 broad classes of elements. So these 3 classes, the metals, the metalloids, and the non-metals, they all have different properties that we need to talk about. But first, a trend that we see is that as we go across the periodic table this way, the elements go from very metallic or super metally. You can think of them as super metally on this side, and they lose their metallic nature as we go across until we get to here where we're in the non-metals, or all of these are non-metals. But that's the trend that we see with these metals and non-metals and metalloids. Okay, but let's talk about the properties of each of these 3 main classes. All right, so I'm going to kind of draw this or write this in a table-ish form. Okay, so we're going to do metals first, then we'll do non-metals, and then metalloids. So metals, hopefully some of you remember this from 9th grade science, because we spent a lot of time doing this, at least with this year's 10th graders. So metals are generally good conductors of heat and electricity. Remember that a conductor is something that allows electricity to easily flow through it. So they're good conductors of electricity and heat. Electricity and heat. So that means that these substances allow heat or electricity to easily pass through them. So that's the first characteristic. Then we have the next one is luster, high luster. Another way of saying this is sheen. That means they look very metallic-y, very shiny. They reflect light very well. the state of matter is that most are solids at room temp, with the exception of one, which is mercury. That's the only exception. All right, most metals are ductile. Well, all metals, we'll say. Metals are ductile, which, remember from 9th grade science, ductile means that they can be drawn into wires. Can be drawn into wires. I don't mean literally drawn, I mean like pulled into wires. So these metals are very good at, you can make wire with this with metals very easily, more easily than you can with metalloids or non-metals. This goes along with malleability. Remember the word malleable. That will say highly ductile and highly malleable. Malleable, remember, means that they can be hammered into sheets. We can make like aluminum foil. We can hammer them into sheets. Into sheets without breaking. All right. Okay, so those are the 5 main characteristics of metals that we need to talk about. Let's look at the same thing for nonmetals. So, rather than being good conductors, they are poor conductors. Poor conductors of heat and electricity, meaning heat and electricity do not pass easily through these types of substances. So, let's look. Sorry, I should have given you an example. All of the yellow ones, these are all metals. Anything yellow is an element that is considered a metal. So sodium is a pretty good conductor. It's not as good as the transition metals, which we'll see later. The transition metals are all these ones in the middle. But you don't need to know that right this second. Iron, nickel, gold, all of these are good conductors. They have high luster and sheen, meaning they're shiny. They're solid at room temperatures, except mercury. They're ductile and they're malleable. So we could make them into wires. They're soft, and they're very easily bent and put into wires or hammered into sheets. Non-metals, on the other hand, are all of these blue ones. All of these blue guys. So the characteristics of these guys are that they are poor conductors. They have the exact opposite characteristics as metals. So they're poor conductors. They're dull in appearance, meaning they're not shiny like metals are. We don't really have a trend for nonmetals. They could be solid, liquid, or gases. Solids, liquids, or gas at room temp. There's no real, it's not the same as metals, like where they don't tell you that on here, do they? No. It's not the same as metals where they're all basically solids at room temperature. All right. And then they have low ductility. They cannot easily be drawn into wires. They break. We won't even say low ductility. We're just going to say that they are brittle, which means they break easily. So that means they have low ductility, or they're not ductile. We're just going to say not ductile at all, not even low. We're just going to say not ductile, can't be drawn into wires, and they're not malleable. They cannot be hammered into sheets without breaking. All right, so those are the characteristics that you need to know of nonmetals. Then we have our metalloids, and our metalloids are just weirdos. They have properties similar to those of metals or nonmetals, and based on the conditions, based on the temperature, based on the pressure, they are more likely to behave like a metal or a non-metal, just based on the conditions that they're in. All right, so they have the properties of both the arrow pointing over here to metals and arrow pointing over here to non-metals, and it's the conditions that determine whether they're more like metal or non-metal. So as the conditions change, so does the element. So for example, Some are shiny, some are dull under certain conditions. Some are solids, some are liquids, some are gases at room temperature. Some are ductile in certain conditions, some are not ductile, or some are brittle. Some are malleable, or some are brittle, some are not malleable, right? So there's no real specific characteristics to metalloids like there are to metals and nonmetals. So if you just remember that all of this little staircase here of metalloids, they're a mix of both. All right, so that's pretty much it for this section. Those are the important things that I think you need to know. So, a way to remember where the metal, I think it's easiest to kind of memorize the metalloids. If you can memorize the metalloids, then you can know, okay, to the right of the metalloids are the nonmetals and to the left are the metals, with the exception of hydrogen, because, of course, hydrogen just has to be a weirdo. So I would recommend kind of making a point to try to memorize this staircase. I mean, that's easier than, it's only 7 elements rather than remembering, oh yes, this one is a metal. Yes, this one is a non-metal. So I would recommend memorizing the metalloids. Okay, so let's go look at your project that you're going to do.
Actually, no, we're going to look at that first thing tomorrow. What I want you to do for the rest of the period today is work on the 6.1 practice problems, and those will be due before the start of class tomorrow. So that is what you're going to do for the rest of the time. Tomorrow we will work on our periodic table project. All right, please let me know if you have any questions about today's lecture. Thank you.